Hey everyone, welcome to this explainer. Today, we're diving into a microscopic mystery that literally drives mechanics crazy every single day: valve body cross leaks. Whether you're an entry-level technician or an automotive student, by the end of our time together, you're going to know exactly how to approach these frustrating hydraulic failures, understand their root causes, and diagnose them like a true detective. Let's get into it.
Here's a quick look at our roadmap for today's investigation. We'll explore the valve body labyrinth, look at symptoms and thermal multipliers, dive into systematic diagnostics and pressure, measure microscopic wear, and wrap up with corrective repairs and prevention. This framework is going to stop you from misdiagnosing mechanical issues as electronic failures.
Section 1. The Valve Body Labyrinth, the Hydraulic Control Center.
Think of the valve body as this incredibly complex, precision-machined aluminum command center. It routes highly pressurized fluid, running up to 20 distinct pressure circuits all at the exact same time. But to solve our mystery, we really needed to find our primary suspect, the cross leak. Now, a cross leak isn't a puddle of fluid dripping onto your shop floor. It's way more insidious. It's fluid secretly bypassing its intended path entirely internally. So instead of cleanly flowing to apply a specific clutch or band, some of that pressure escapes into a totally different circuit, and that throws the entire system into complete chaos.
So what keeps these circuits perfectly isolated in the first place? Well, it's basically a system of microscopic gates and walls. Spool valves use incredibly tight tolerances to seal their bores and route fluid. Then you've got checkballs acting as one-way flow controls. And finally, separator plates, which are wedged right between the castings, ensuring that only very specific passages are allowed to communicate with each other.
Now here's where the stakes get really high. If those spool valves wear down or a checkball fails, you don't need a massive catastrophic blowout to completely ruin the transmission's behavior. Honestly, a tiny 5 to 15% pressure loss in an intended circuit is more than enough to completely disrupt the transmission's shift logic.
Moving right along to Section 2, symptoms and thermal multipliers connecting macro symptoms to micro leaks.
What does a cross leak actually feel like behind the wheel? Your very first clues in the shop are going to be these macroscopic driving symptoms. For instance, a shift flare. That happens when an outgoing clutch releases before the incoming one has enough pressure to hold it. Or maybe torque converter shudder. It kind of feels like an engine misfire, but what's actually happening is the clutch is partially slipping because pressure is bleeding between the apply and release circuits. You might also see a delayed, mushy engagement when dropping into gear, or experience really harsh, clunking shifts when a cross leak accidentally applies two clutches at the exact same time.
Here is the trap you absolutely have to avoid. Do not be fooled by the false suspect. Cross leaks perfectly mimic electronic faults like a bad solenoid. What happens is the ECU notices the transmission slipping, so it maxes out the line pressure to compensate, and then throws a totally misleading electronic code. Far too many transmissions get rebuilt unnecessarily because a tech was busy chasing a ghost electronic fault instead of recognizing the true culprit, microscopic bore wear, causing an internal cross leak.
And when those clutches slip, heat, lots of it. They generate a massive amount of friction. If you're looking at your data and you see fluid temperatures hit 240 degrees Fahrenheit, you have officially entered the severe damage threshold. Heat is the ultimate enemy here. It completely destroys the ATF and rapidly accelerates the wear inside that valve body.
Which leads us right into the thermal multiplier effect. You know, that classic customer complaint, right? Hey, it drives fine in the morning, but shifts terribly on my commute home. Well, here's exactly why that happens. Cold, thick ATF actually masks worn bore clearances. It acts like a Band-Aid, but as the transmission heats up, the fluid's viscosity drops, it thins out, and that hot, thin fluid slips right past those worn spool valve lands, making the cross leak drastically more severe at high temperatures.
Section 3. Systematic diagnostics and pressure, building your investigative framework.
All right, so how do we trap this thing? You need a rock-solid, systematic diagnostic path. First up, interpret your scan tool data. You're looking for specific gear ratio error patterns to point you in the right direction. Second, hook up your gauges for line pressure testing to see if the main system is struggling. Third, do systematic air check tests on individual clutch circuits to isolate the leak. And finally, you want to use vacuum testing directly on the valve body. That is the absolute most accurate method to pinpoint the exact worn bore causing all your headaches.
When you're testing, you're constantly comparing your diagnostic pressure readings against healthy OEM manufacturer specifications. Putting these numbers side by side helps you really visualize the pressure drop. Check out reverse on this chart. It requires a massive 180 to 280 psi to operate correctly. That's exactly why a delayed reverse engagement is so often one of your very first early warning signs of a cross leak.
Look,
The scan tool can totally lie to you with a false code. But the pressure gauge, it never lies. If you see a deviation of just 15 to 20 psi from those OEM specs in a specific circuit, you've got your confirmation. You have a major internal sealing failure, not a bad sensor.
Section 4. Microscopic wear and measurements. Measuring the invisible culprit.
Once we actually pull that valve body, the physical hunt for microscopic damage begins. Take a look at this number. 0.003 inches. That's roughly the thickness of a human hair, or about 76 microns. That tiny measurement is the maximum allowable failure threshold for bore wear before catastrophic pressure loss kicks in. Anything worn beyond that, and the fluid just slips right past the valve lands.
Because we're dealing with tolerances that tight, you absolutely cannot just eyeball this stuff. You have to use precise, calibrated bore gauges. Measure the diameter at the top, the middle, and the bottom of the bore, and then calculate that clearance against the spool valve land to verify it against the manufacturer's wear limits. What you are really hunting for here is oval or egg-shaped wear. That happens because pressurized fluid constantly sideloads the valve against the bore over thousands and thousands of miles. But hey, don't get tunnel vision on just the bores. You always need to add a step to inspect those steel separator plates and gaskets. Severe overheating can warp the plate, and that constant high-pressure fluid flow can actually physically erode the stamped orifices. If a hole is eroded more than 0.005 inches, or the plate itself is warped more than 0.002 inches, fluid is going to bypass its intended route, permanently connecting adjacent passages that should be isolated.
Section 5. Corrective repairs and prevention. Fixing the root cause.
So, we found the true culprit. How do we actually fix it? You've got a few solid solutions. For known high failure areas, you can use targeted drop-in bore repair kits, like the ones from Sonex. For a more permanent comprehensive fix, machine shops can perform bore sleeving. That's where they machine the worn bore oversize and press in a precision stainless steel sleeve. Or you can just opt for a full valve body replacement with a remanufactured and fully sleeved unit. Every single one of these solutions restores that hydraulic sealing right back to exact factory specifications.
Of course, preventing this from happening in the first place is the ultimate goal. Ultimately, all of this microscopic wear we've talked about, the scoring, the orifice erosion, the egg-shaped bores, all of it is massively accelerated by degraded, dirty fluid. Managing heat and keeping clean ATF running through that transmission is literally your absolute best defense. And that means having real conversations with your customers about proper fluid maintenance intervals. For normal, everyday driving, advocate for fluid changes every 50,000 to 60,000 miles. But for severe service, we're talking heavy towing or constant stop-and-go city traffic, that interval drops to 30,000 to 40,000 miles. Getting that fresh fluid in there replenishes the anti-wear additives and prevents the thermal degradation that thins out the fluid and destroys those microscopic valve clearances to begin with. Which brings us to the big question for you to take away. Is your next rebuild actually fixing the root cause, or just delaying the inevitable next failure? By mastering pressure testing, understanding what your scan tool data is actually telling you, and performing proper microscopic bore measurements, you guarantee that you're solving the cross-leak mystery for good. Don't fall for the false electronic suspects. Fix the root cause and stop putting band-aids on broken hydraulic labyrinths.